Hello everyone, my name is Kenneth Rapetsoa, and today I'll be telling you about one of the programs that we have at the Mandela Mining Precinct under the Advanced Ore Body Knowledge Work Package 4.3, which is tunnel seismic prediction. So to get started with this, the tunnel seismic prediction is a collaboration between the Mandela Mining Precinct and the Wits Seismic Research Center, where the Mandela Mining Precinct is trying to create what they call a glass rock environment. And this glass rock environment involves locating where the reef is and establishing the metal content in that area and what extraction processes they can do. So the Wits Seismic Research Center took on this challenge to then investigate the technologies that can be used to obtain the information ahead of the phase in the mining environment. This collaboration involved institutions such as CSIR, GeoLink, and Open Ground. So as we all know, the South Africa hosts some of the deepest mines in the world, with 8 out of 10 of these mines being from South Africa, with Mponing being the one of the deepest one at about 4 kilometers deep. And this comes with challenges such complex environments, complex geology, then creating complex mining processes that are there. And some of the fundamental challenges faced in these South African deep mines is how do we optimize extraction and how do we mine safely in this environment. So then the Wits Seismic Research Center, as I've mentioned, it took on this challenge, and what they started working on is the tunnel seismic prediction in the Wits gold mines and the platinum mines. So they started by designing seismic models for underground experiments and surface experiments. So these underground models will then help them in designing in-mine experimental seismic studies. So this research involved the use of multiple sensors and multiple sources. Some of these sensors being innovative technology such as the remote acquisition unit, the broadband seismometer, the lens streamer, and the conventional geophones that we all know. And then they also had multiple sources such as accelerated wave dropper that differed in the capacity that they can put, that differed in energy input that they can put into the ground. They also had a smaller source, which is just a sledgehammer. So they conducted research underground and also on surface, with the diagram shown here showing you some of the lines that they conducted, the seismic lines they conducted underground, with multiple configuration of the geophones and multiple experimental setups, with some of the lines being short, some of the lines going to a length of about 300 meters. So these lines that we had also had multiple geophones that we used, where you had geophones that range from 4.5 hertz. We had geophones that are 100 hertz. And also we had what we call Michel's pillar, which was the target at that area in the Maseve mine. So that target, as I've mentioned, we conducted multiple configuration where we put some of the geophones on the wall, on the face, on the ground, and some of these geophones passing through spaces that had water. As you can see, the diagram here shows you one of the setup that we put up, which was experimental, where we put the lens streamer on the side wall with being supported by the roof bolts, which was something that I believe was not done in South Africa. So this innovative technologies, combining this technology is very crucial for successful seismic data acquisition, and also it opens up possibilities of conducting these experiments in a cost-effective manner and environmentally friendly active and passive seismic surveys. So moving from collecting the data, then the data will then be processed, and it will provide high-resolution images that will give us an idea of what is happening ahead of the phase and what is happening underground and just a few meters ahead of the mining phase. And this will give us valuable information on the targeted pillar. Thank you.